All right, guys, so we are just going to finish up kind of what we already did in class about kind of defining these 6 functions that are really going to be the basis for this whole course. So let's just kind of write this down and maybe define a couple things, get it all in kind of one spot, and then we'll do some examples. We'll talk a little bit more about exact angles. So we talked about the 30 and the 60. We'll also talk about the 45 because those actually have pretty nice, relatively nice sine, cosine, and tangent values that we can actually find the exact form for. So we're going to talk about that. We're also going to maybe chat a little bit about how could I find an angle if I know, that the cosine of that angle is 1/2. Could I figure out what that angle is? So let's summarize this a little bit. I want to remind you, if I have a triangle, a right triangle, oh man, you're going to really have to, remember I told you kind of this was a lesson in imagination. You're going to have to do that, pretend that these are all straight lines. And it doesn't actually matter where I put theta, but if I put theta right here and this is a right angle, then when I define this triangle, again, remember we called this I'm going to use OPP for opposite. I'm going to do ADJ for the length of the adjacent side, and then the hypotenuse, which we'll just call HYP, is the length of the hypotenuse, which is always the side opposite of the 90-degree angle. Okay, and so our 6 trigonometric functions. So let me go back and erase that really quick. There we go. Sorry, getting back into this after break. Yeah, there we go. So these are our trig functions or trigonometric functions. I'm lazy enough that I'll say just trig if that works for you. And this is going to be quite important. I'm going to say of an acute angle. So remember, an acute angle is an angle that is between 0 and 90 degrees, okay? Between 0 and 90 degrees. So let's kind of write this down more as the definition. So let's let theta, okay, be an acute angle of a right triangle. Okay, so if we have that, a right triangle that is, and some angle in that right triangle that's not the 90-degree angle, then we define the following. Then we define the following functions. And remember, well, let's talk about that again in a minute. It's so exciting that I get a little bit ahead of myself. So those 6 functions, right? Anytime I talk about the 6 trig functions, we're going to talk about sine. So that's one of the trig functions. So sine of theta, S-I-N-E of theta. If we look at that shorthand, that's S-I-N theta, and that's what you'll see in your calculator also. So the definition of the sine of theta, remember, it's a ratio of sides of that triangle. So wherever theta is, sine is always going to be the opposite side, the length of that opposite side, okay, divided by the length of the hypotenuse. And that gives us a number. This number doesn't have any units on it. This number, well, I guess it could have units on it, but this number really is just a ratio between 2 sides, right? So sine is one of the functions. Cosine is another one of the functions. The abbreviation for cosine is COS of theta. How do we find cosine? We take the adjacent side to theta, so that would be this side right here, and I'm going to divide it by the hypotenuse, okay? And then finally the tangent of theta. So tangent of theta, which we abbreviate TAN. Remember, you must have this theta here. Sine, cosine, and tangent are functions. We have to be taking the function of something, okay? Just like you would never just leave a square root without taking the square root of something, this by itself really doesn't make sense in math. We have to be taking the square root of x or the square root of 16, right, of something. Same thing, just this as is. Anytime, if you see put sine equals, technically in mathematics that doesn't mean anything, okay? You have to make sure that you're taking the sine of an angle, right? You're taking the sine of 20 degrees. You're taking the sine of pi over 6, something like that, okay? Tangent then is just going to be opposite over adjacent. So tangent is the only one that does not involve the hypotenuse. Okay, so those are my three kind of, I don't want to say normal functions, that doesn't make any sense, but those are my three kind of base functions. Okay, then remember we had three other ones. Sine, we had the cosecant. Whoa, all right. This is the cosecant of theta, right? Cosecant is abbreviated CSC of theta. And it's basically we just flip what we do with sine. So it's hypotenuse over opposite, which is basically the reciprocal, not just basically it is, it's the reciprocal of sine. So it's 1 over sine. I'm sorry, I'm running out of room here. Then we have the secant of theta, which we abbreviate SEC of theta. That is going to be the reciprocal of cosine. So that's going to be hypotenuse over adjacent. I honestly don't really memorize these. I just remember that secant is 1 over cosine. Oh, I'm running out of room here. So let me kind of move up here really quick. Okay, so now the last one, sorry, that should go down here, is going to be tangent. The reciprocal of tangent. The reciprocal of tangent is called cotangent of theta. Okay, cotangent of theta, and we abbreviate that COT of theta. Again, that's a reciprocal of tangent, so this is adjacent over opposite, or another way to say that, oh man, I really should have planned this out, is 1 over tangent of theta. Okay, so those are my 6 sine, cosine, and tangent. Those are kind of the main 3. And then 1 over sine is cosecant, 1 over cosine is secant, and 1 over tangent is cotangent. Okay, those are my main 6 trig functions. Remember that these trig functions are just ratios of sides of triangles, and we're defining them to be such. And I've been throwing around this word function, right? And we kind of talked about this, but saying that something is a function, I mean, you're putting some pretty big weight on that statement. So remember what a function is. It's saying for every input, there's one and only one output. So when I talk about the sine of 30 degrees, the sine of 30 degrees is going to be a number. It's actually going to be 1/2. It will always be 1/2 no matter what triangle we are in. So let's go to some examples. Maybe. There we go. Okay. So a quick example, find the 6 trigonometric values. Okay, so I'm lazy, I'm just gonna put trig. So find the 6 trig values of alpha and of beta given the triangle below. All right, so given the triangle, and let's draw ourselves a triangle here. I always draw my triangles with my right angle to the left, so I'm gonna try and do this another way. Let's let this angle be alpha. Let's let this angle be beta. And you know, we have some Pythagorean triples, so I have to be careful. I can't just kind of throw whatever numbers I want on this because I want it to be a right triangle. So if it's a right triangle, of course, it has to satisfy the Pythagorean theorem. And, you know, maybe one of our easiest ones to use then is a 3, 4, 5 triangle. All right, so let's start with alpha. So alpha, let's find the 6 values of alpha. So if I look at sine of alpha, myself a little more ink flow here. Sine of alpha, okay, again, what is sine? So, all right, so here's, you may have heard us say SOHCAHTOA. Here's a little quick way for you to remember what is what, okay? And I love devices like this where it helps you remember things. So SOHCAHTOA is SOHCAHTOA. You got to remember how to spell so and ka and toa. If you don't remember SOHCAHTOA, how to spell that, this is what my math teacher said when I was in high school, which wasn't very long ago, right? Well, okay, maybe it was a while ago. By this math teacher who was really wonderful. His name is Mr. Oliver. And he just had the most dry sense of humor, and he was hilarious. But he taught us this. One way to remember this is some old horse caught another horse taking oats away. And I know that sounds silly. Some old horse caught another horse taking oats away. But it helps you remember this. And what does the SOHCAHTOA mean? Well, I'm going to tell you. So this S right here represents sine. And what is sine? It's opposite over hypotenuse, okay? And then this C right here, that represents cosine. And what is cosine? That's adjacent over hypotenuse. So do you see how that kind of tells us which way it goes? And then what does T stand for? That's tangent. What is tangent? Opposite over adjacent. Whoa. And you're going to need to know those, right? So SOHCAHTOA is kind of a nice way of figuring out, or some old horse caught another horse taking oats away. So you go to take a test, you write down SOHCAHTOA, and then of course to find the reciprocal functions like cosecant, secant, and cotangent, you just flip those. So back to the problem at hand. Sine of alpha. Here's my alpha. What is the opposite side? In this case, it's 3. What is the hypotenuse? It's 5. So the sine of alpha, I don't know what alpha is, but I know that the sine of it, based on the triangle I'm given, is 3/5. So again, this is a function. My input is alpha. I don't know what that is. We can find it later. My input is alpha. What does this function spit out? It spits out the number 3/5. Okay. Cosine of alpha. So these are pretty easy. It's just a matter of memorizing what they stand for. Remember, cosine is adjacent over hypotenuse, so I'm going to alpha. What's my adjacent side? It's 4. My hypotenuse is 5. And then tangent of theta, or not theta, alpha, right, so here's my alpha. Opposite is 3. What's adjacent, right? Opposite adjacent is 4. So my tangent is 3/4. So when I go to find all 6 of these trig values, I find my original 3, right? Which is the sine, cosine, and tangent. And then I'm going to go and find the reciprocal functions. So the reciprocal of sine, I want it to be secant, but I know it's not. I know it's the opposite letter, because it'd be way too easy if it was the same. So cosecant is going to be the reciprocal of sine. So I'm just going to literally flip that value for sine, and I get 5/3. Secant of alpha, okay, is 4. That's 4 over 5 is cosine. So I'm just going to flip cosine, and I get 5/4. And then tangent, the reciprocal function of tangent is cotangent. So again, I'm just gonna flip it. Flip it good. Yeah? That makes sense. It should be pretty simple. Beta, again, these are pretty simple. It's just a matter of remembering, right, that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse. You're gonna need to know that. So let's get beta. So sine of beta. So now I'm looking at beta, and I'm kind of now looking at this triangle from a different point of view, right? So what side is going to be opposite? So sine is opposite over hypotenuse. The side opposite beta is 4. And again, the hypotenuse is 5. Cosine of beta. Now the adjacent side to beta is 3. And the hypotenuse is 5. And then the tangent of beta, right? If you look at the tangent of beta, opposite is 4. And 3. Okay, so now again, cosecant of beta then is just going to be the reciprocal of sine, or 1 over sine. So I get 5/4. Secant of beta is the reciprocal of 3/5, or 1 over 3/5, which is 5/3. And finally, cotangent, of beta, I'm just going to flip that. Oh, speaking of Mr. Oliver, he would never let us write our fractions like that. Fractions always had to be written vertically. I understand why he did it. You know, if you have like 3, if you have this, is that 3 over 4x, or is that 3/4 x, right? So I understand why he didn't like, we could not write fractions like that. We always had to write fractions vertically. Oh man, he was great. And I hated it, of course, in high school, but it was a really good thing, honestly, when I got higher in math. Hope that makes sense. That should be pretty straightforward. We can also go the other way. So what if, for instance, I tell you something about a certain angle? Could you find the other values of that triangle? Okay. So actually, before we get there, what I want to point out really quick, and we saw this in class, right? When we all drew that 30, 60, 90 triangles. So for example, that 3, 4, 5 triangle, oh my goodness, I cannot draw a straight line to save my life. So let's say I did have a 90-degree right, triangle. And, you know, actually, let's do this. Oh man, I can't do that. Remember I said it's going to be a bit of a lesson in imagination. It is. So if I have like a 3 here, 4 here, and a 5 here, and this is my angle theta, if I took that, let's say I took that same angle right here, and I'm just going to take those sides, and I'm going to multiply them by 2. Okay, so this distance right here, I'm actually going to increase by 2. This distance right here, remember this is not going to be perfect. And then this distance here, I'm going to increase by 2. If I do that, that angle is going to stay the same, right? So that's still going to be theta. This is just going to be 6. This is going to be 8. And this is going to be 10. So notice if I look at the sine of theta, remember a function for every input, there needs to be one and only one output. If I look at this triangle right here, right, what would the sine of theta in this case be? The sine of theta in this case would be opposite, which is 3, over hypotenuse, which is 5, right? Sorry if you can't see that very well. 3 over 5. And then if I look at theta in this case, right, what is the sine of theta in this case? Opposite is going to be 6 all over 10. Notice, my friends, that 6/10, right, is exactly the same as 3/5. So a very important point, and you should put this in your notes, is that trig values, right, only depend on the measure of an angle, not on the size of the triangle. Not on the size of a triangle. So we know that similar triangles, right? Similar triangles have exactly the same angles. So similar triangles are gonna, those acute angles in those triangles are gonna have the same sine and cosine values because we know that they have the same angles, right? It doesn't matter the length of the sides. Remember, we saw that when we all graphed or drew our own triangles, but that's an important thing to remember, is that the sine of 30 degrees will always be 1/2 no matter what triangle you're in. Okay, so let's go ahead and do another example. What if I'm giving you, let's get crazy here. What if I give you, whoops, heaven forbid I use a different color than, I'm a creature of habit. So let's say if the sine of theta, okay, let's say, is equal to 12 over 13, and theta is an acute angle. Okay, find the remaining 5. Oh, I forgot an N in there. Whatever. Remaining 5 trig values of theta. Okay. So we know that the sine of theta is going to be 12 over, or is 12 over 13. Again, I don't know what theta is, and that's okay. But what I really recommend you doing here is just drawing a triangle. What do I know? I know that sine is opposite over hypotenuse. So I'm just going to sketch a quick triangle. Obviously, it's not going to be perfect. Doesn't even matter. I always put my right angle on the left, so now I'm going to put it on the right. I mean, I could even do this, right? It honestly does not matter as long as you're consistent with how you label opposite. I don't like that triangle now. As long as you're consistent with how you label opposite and hypotenuse. Oh, look, and then I just went to the right. All right, so there's my right triangle. It doesn't matter either which one I label to be theta. So I'm going to put theta down here. But what I do know is I know that sine is opposite, right? SOHCAHTOA over hypotenuse, some old horse. That's my some old horse part. So I know I can label this triangle. I know that the opposite then is going to be 12. The length of the opposite side is 12. And I know that the hypotenuse is 13. Now, how are we going to be able to find my adjacent side? I'm definitely going to need my adjacent side for anything involving cosine and tangent. And so, well, what do I know? I know I have this good buddy Pythagoras, right, who probably didn't even come up with the theorem himself. But but got all the credit for it. So I have the 12 squared. I'm going to just use the Pythagorean theorem. 12 squared plus b squared equals 13 squared. I'm pretty sure it's 5, but let's just make sure. 13 squared is 169 minus 12 squared, which is 144. Yeah, we get 25, and the square root of 25. I don't need a plus or minus in this case. We are going to worry about the plus and minus eventually, but in this case I don't need it because we're just talking about a triangle with a distance, okay? So b is equal to 5. And so now we're ready to go, man. We're cooking with gas. So I know sine, I need the remaining 5 trig values. So cosine of theta then, what's my adjacent? It's 5. My hypotenuse is 13. Tangent of theta, if I look at where my theta is, opposite over adjacent, so that'd be 12/5. Okay. Secant of theta, I guess I should have done cosecant, but secant of theta, I see it right here, it's just 13/5. Cosecant is 1 over sine. Well, I know sine, that was given to me, that's 12/13, so that's 13/12, and then cotangent of theta is 5/12. Again, as you're doing these, if you need to, write down your SOHCAHTOA. Some old horse cut another horse, taking notes away, right? So that you can really see what those definitions are. Good. We don't always have perfect numbers either. I mean, guys, what in life is perfect? Not many things as far as I know. Haven't found one thing in life to be perfect. So what if we had something like this? So same example, given, and let's just, again, I'm going to assume that beta is acute. I know what assuming does. But given that the tangent of beta, let's say that the tangent of beta, I don't know, what do I want it to be? Let's have the tangent of beta be 1 over, I kind of want to make this interesting. Let's do 1 over 7. I don't know. This will be interesting. Given that the tangent of beta equals 1/7, again, beta is acute. Find the remaining trig values. Remaining 5. Trig values of beta. Okay, so again, I'm going to draw a triangle. I know opposite is 1. I know adjacent is 7. So I'm actually going to try and draw this a bit to scale. You don't have to do that. You know, it doesn't have to be that way. We're not dealing with theta. But I'm trying to be good here. This is beta. That means this is 7, right? Because I know that tangent of beta is going to be opposite over adjacent, right? Which is 1 over 7. Okay, so let's see what we're going to get. So I need my hypotenuse definitely to get the rest of these. So 1 squared plus 7 squared, that's 1 plus 49, which is 50, right? And so what is my c squared then is going to be 50. So what is c? It's the square root of 50. And I wanted to do this one because it's just a little more interesting. I do want all of your radicals simplified. Again, I don't really care about rationalizing denominators, but I think because of the ACT and because of my math lab, we'll maybe spend some time with that. But square root of 50, I definitely don't want you to leave it like that. There is a perfect square that's a factor, and that's 25. So we actually get 5 root 2. So what is this? This is 5 root 2. And this is going to be, what I'm looking for here are the exact values, right? The exact values of the 5 trig. And when I say exact, that's what I mean by 5 root 2. Approximate would be actually plugging it into our calculator and getting a decimal. That's an approximate answer for 5 root 2, which is an irrational number. All right, so let's go. So sine of beta then is going to be opposite, which is 1 over my hypotenuse, which is 5 root 2. Okay, so remember to rationalize denominators. So what is the guy that's causing us problems? The guy that's causing us problems is the root 2. So I'm going to multiply the top and bottom by root 2. Okay, once I do that, what I get on the top is root 2. On the bottom, I just still have that 5. And then I have root 2 times root 2, which is 2. So what is the sine then of beta, all nice and pretty with a little bow around it, is square root of 2 over 10. And that's all you can do. Don't cancel the 2's or, you know, get crazy on me with that. What about the cosine of beta? Cosine is going to be adjacent, which is 7 over 5 root 2. Again, do the same trick, multiply by root 2. I'm going to get 7 root 2 all over 10. Same thing. We already got tangent, so we're good to go there. Tangent's 1/7. What about my reciprocal functions? So cosecant of beta now. Now, when I'm doing cosecant of beta, be mindful if we're worried about rationalizing. I'm not going to flip this one. Do you see that? Because what that's going to do is put my square root in the bottom. I'm going to come up to my original one for sine. I have 1 over 5 root 2 for sine. So if I flip that, I get 5 root 2 over 1, also known as 5 root 2. What about secant? So secant of beta, that's going to be the reciprocal of sine. Again, same thing. I'm not going to flip this one. I'm going to go back to my original one and flip it because that puts the square root in the top and I don't have to worry then about rationalizing the denominator. So secant of beta will be 5 root 2 over 7. And then because tangent's 1 over 7, that's pretty easy. Cotangent of beta then is 7 over 1, also known as 7. Good, and that's how we find those trig values. You know, life isn't always nice rational numbers. Life sometimes is irrational. I'm going pretty deep here, you know, philosophically. So that's what we get when we deal with something like that, which is great. All right, guys. So a couple more things. What we need to talk about now are some specific angles. So we're gonna get into geometry just a tiny little bit. Don't get sad about that. We're gonna look at the trig values of 3 angles, and you're gonna need to know these values. Okay, so you're going to need to know at least. So what I want you to know is sine, cosine, and tangent, and then you can find the reciprocal functions of those. But we need to know the trig values of 30, 45, and 60 because these are unique because of the Pythagorean theorem. These give us like really nice, these are rare angles where we can actually find the exact value for sine, cosine, and tangent. Usually we can't find that exact value. So if I have like an angle of 42 degrees, I don't actually have a nice way to write that exact. I would actually have to just, you know, we can put that in our calculator and we can draw a triangle with a 42-degree angle and then find some sides and find those ratios, but they're not going to be exact. We're going to have fractions, or not fractions, excuse me. We're going to have irrational numbers, but something like 30, 45, and 60, I can actually find the exact value. Not that I said that wrong, but we'll have to approximate it. Irrational numbers can still be exact. So let's talk really quick about 30 and 60 right away, because 30 and 60 I can kind of kill 2 birds with 1 stone here. So let's look at 30 and 60. So what I'm going to draw first to try and figure out these trig values. So remember, these trig values only rely on the value of the angle. I need you to keep that in mind. They only rely on the value of the angle, and it does not rely at all on the size of the triangle. So I'm going to pretend that this is a triangle. Well, it is a triangle kind of, but look at, oh, that's so bad. I'm going to get an equilateral triangle, okay? So an equilateral triangle has 3 60-degree angles, and I know that this angle right here is 60 degrees. I'm just not writing that because I'm going to cut it in 2. So notice, so another thing that you need to be very careful of, if I have this triangle right here, I can't talk about sine, cosine, and tangent right now in this triangle because sine, cosine, and tangent are all defined in a right triangle, which has a 90-degree angle. This guy doesn't have any 90-degree angles. So what am I going to do about that? Well, let me tell you, I'm going to do it right now. I'm going to take this triangle and I'm going to cut it in half. Man, that's a horrible triangle. So just pretend. If I cut this in half, I'm going to take this side because this looks more real. Look at what I get. So if I cut this in half here, draw the altitude, I think. Oh man, my geometry rules are lacking a bit. But if I cut this in half, right, look at what I'm going to get. If I cut that angle in half right there, then I'm going to get a right triangle by drawing the altitude. And I have then a 30, 60, 90-degree triangle, and I can figure out now, remember, it doesn't matter the size of the triangle, it just matters the measure of the angles. So if I can figure out, given the triangle that I've drawn right here, if I can figure out my opposite and adjacent and hypotenuse for this triangle based on what I know, then I know we're going to be golden for anytime we want to use 30-60. So this is an equilateral triangle, so to keep things simple, I am going to set this distance right here. I could set it to be whatever I want. I could set it to be smiley face if I want. I could set it to be 419. But to keep things easy, I'm going to say that this distance is 1, right? So what does that mean? That means that this whole distance is 1. Remember, this is supposed to be an equilateral triangle. And that means that this whole distance right here, right, is 1. Okay, so if that's true, then I know a couple of things. So if that's true, well, this is 1, okay? And, oh, actually, I don't want it to be 1. I lied. Jeez, I lie a lot. Sorry. Sorry. I'm actually going to set it to be 2. I would have known that if I had, like, written notes. But, all right, I'm going to set it to be 2. I am so sorry about that. I want it to be 2. The reason I want each side to be 2, remember, I can choose whatever side I want. Or whatever length I want, is that then when I cut this in half, I really just care about this yellow triangle right here. So what would this distance be? Well, pretend, right? If I cut that in half, then this distance right here would be 1. I don't want to deal with a fraction. So this is going to be 1. What is my hypotenuse here going to be? This is just going to be 2, right? Because it's the same as just the side of the equilateral triangle. And then if I do a little bit of Pythagorean theorem, I get 1 squared plus b squared. So this is going to be my height right here, equals 2 squared. So what is b? B squared is 4 minus 1, which is 3. So what is that altitude there? It's the square root of 3. Okay, and draw this over here a little bit better. Okay, so here's what we got. We got 60 here. We have 30 degrees here. And then I've defined this to be 2. I've defined this to be 1. And this to be square root of 3. I haven't really defined that. That's by nature of taking that equilateral triangle and basically cutting it in half and then setting each side of that equilateral triangle to 2. I could have set it each side equal to 1. It wouldn't have changed anything. It's just I don't get the fractions right away. And so I want to deal with the fractions maybe later. Okay. So now that I have this triangle set up, that I know that these lengths are true for this type of 30, 60, 90 degree triangle, I am ready to actually find the values of sine, all the 6 trig values of 30 and 60. So let's start off right now. I'm actually going to make a little chart here. Okay, so I have sine of theta, cosine of theta, and we're going to fill in this chart. Okay, so write this somewhere, where you can kind of come back to it, because this is going to be a pretty big deal. Not gonna lie. Why can I draw kind of straight lines now? And then what's my theta? So my theta, we want to find the theta of 30 degrees. I want to find the trig values of 45. We'll get to 45, but let's just put it in our chart right now. And I want to find the trig values of 60 degrees. Okay. All right. So let's do the 30 and 60. We can do that right now. And then we'll talk about the 45 degrees. 45 degrees is pretty easy because we just are going to have an we're going to have an isosceles triangle. So here we go. All right, so let's look at 30 degrees. Let's come back up to my triangle over here. Remember sine of 30 degrees. So I'm going to pick this angle right here, and I'm going to look at the opposite over hypotenuse. So opposite of 30 is 1. And the hypotenuse is 2. And remember, we found that. We found that today when we did our triangles. We were really, really close to 1/2 for the sine of 30. What about the cosine of 30? Adjacent of 30 is root 3. We had seen that. And the hypotenuse is 2. And then what's the tangent of 30 degrees? Tangent is opposite over adjacent. So that's 1 over root 3. Again, I will accept that. Or if you multiply the top and bottom by root 3, you get root 3 over 3. That might be, maybe you just should rationalize. Let's skip 45 and let's go to 60. So now I'm going to come over here and look at 60 degrees. Okay, what is the opposite of 60? The opposite in this case is going to be what? Root 3, right? And my hypotenuse is 2. If I look at 60, now the adjacent is actually the 1, and so the cosine of 60 is actually 1/2. And then the tangent of 60 is opposite over adjacent. That's root 3 over 1, which is just root 3. And you notice, right, there's some correlations here. And that is because 30 and 60 are complementary angles. Okay, so the sine of 30 is the cosine of 60. And the cosine of 30 is the sine of 60. Okay, so that's one way that you can remember those. Actually, when I remember these, really if I can just remember that sine is the sine of 30 degrees is 1/2, I can figure out the other one. So if the sine of 30 degrees is 1/2, then the sine of 60 is the other one. If the sine of 30 degrees is 1/2, then the cosine of 30 is the other one, right? And then a trick for tangent, and we'll talk about this in a little bit, but tangent is actually just sine divided by cosine. So if you take sine and divide by cosine, these 2's would cancel out, and we'll talk about that later, but just take that's why you write sine on top and then cosine. Take the numerators, and you would get opposite is the numerator of sine, adjacent is the numerator of cosine, and just make a fraction out of them. So I would get 1/√3. I hope that makes sense. Cool. All right, so let's really quick look at the 45. So again, you're going to need to know these. We will probably have a non-calculator part of the test, or we may even have some of the test be non-calculator period. But let's look at a 45-degree angle. So if I have a triangle with a 45-degree angle, oh man, oh, why are those hypotenuses? Hypotenuses? So hard to draw. This is not perfect, I apologize. But this is 45 degrees. What would that make the other angle? Well, 90 minus 45 is 45. And so what does that mean? That means that this must be an isosceles triangle, right? Because these two angles are the same, that means the length opposite those two angles must be the same. So I need to pick a number for those opposite angles. Because remember, the trig values only depend on the measure of the angle and not the size of the triangle, okay? So I'm going to go easy here. I know I tried to be easy on my the last one, but I'm not cutting this guy in half or anything. So I am going to say, okay, I'm going to let this side be 1. What does that mean? I know this side must be 1. Also, that goes from geometry. Again, if I have two angles that are the same, it's an isosceles triangle. So the two sides are the same. And then if I just do a little bit of Pythagorean theorem, I mean, who doesn't like a little bit of Pythagorean theorem in the morning, you know? I get 1 squared plus 1 squared, that's 2. That's what my c squared is. So the square root of 2 is going to be what my hypotenuse is. Again, you guys, you could set this up and you could make this 17 and make this 17, and you're going to still get root 2 times 17 over here, okay? We're going to get the same values no matter what. Again, it doesn't matter the size of the triangle. It matters what the angles are. So now that we've, and a lot of people actually, this is something you can do as well. You can just memorize this triangle and memorize this triangle right here, and you could write those two triangles down, and then you know all of this chart just by having these triangles and knowing SOHCAHTOA. Okay, so let's look at sine. 45 degrees, it doesn't matter which one I take, right? They're both 45, so let's just take this one. Opposite is going to be 1. Hypotenuse is root 2. So that's 1/√2. Multiply top and bottom by root 2, we get root 2/2, okay? So either 1/√2 or root 2/2. My math lab, ACT, stuff like that, do root 2/2. Cosine, same thing. Adjacent is 1, hypotenuse is root 2, or we also 1/√2 or root 2/2. And then for tangent, I get 1/1, also known as 1. Also, you can see that trick again. If I take the numerator of sine divided by the numerator of cosine, do you see I get root 2 divided by root 2? Actually, if you just take sine and divide it by cosine, because the denominators cancel, they're going to have the same denominator no matter what, because the denominator is hypotenuse on both of those. You need to know this chart. Write it down. Come to know and love it. Become friends with it. Write it down a bunch of times so that you know these. Okay, so on the tests and stuff, I'll be asking for exact values of sine of 30, sine of, any of these of 30, 45, 60. And you need to know those. Okay? Okay, perfect. I love it. Great. What else? So what if we didn't have 30, 45, or 60? So, I mean, the good thing is, and I won't spend too much time on this because we're almost 40 minutes already. So what about not those? So what about evaluating something like the sine of 47 degrees? Okay, so the sine of 47 degrees, I can't easily draw a triangle with a 47-degree angle where I know what the sides are. So I can't use the fact of an equilateral triangle. Its other side wouldn't be, an isosceles, right? Its complementary angle wouldn't be. So this is where our calculators come in, which is great. And so if you go on your calculator, go to your TI-84. Well, let me show you. There are a couple important things that you need to do in your calculator, and you're going to be able to do this right away. But the big thing here is that making sure that you're in the correct mode. So go ahead and go to mode, and you want to make sure that you're in degrees. We will talk about radians later on, but when you use your calculator for right now, come down to mode, go over to degree, press enter, and get out of there, because we're going to be in degrees for right now. So when I quit, right, I'm going to get the sine then of that 47. So there's your sine button right there. Remember that sine inverse is not 1 over sine. That's the inverse function of sine, and we'll talk about that here in a second. So sine of 47 degrees, then what are we going to get? We're going to get some number because I can't find the exact value of that. So sine of 47, 0.731353716, and we can round it. I'll make sure to tell you what to round it to, okay? You can also check yourself on some of these. This is why I will have a non-calculator part of the test. I know that the sine of 30 is, oh wow, there is my music. I know that the sine of 30, there it goes again, sorry. I know that the sine of 30 is 1/2, so sure enough, I get 1/2. Sine of 60 I know is root 3 over 2, so we'll get kind of used to seeing that root 3 over 2 is about 0.866. So I hope that makes sense. We can put numbers in here. Again, the main thing to realize is in my mode, I need to make sure I'm in degree for right now. We will talk about radians later on in this class. All right, so again, you know, we have that is 0.73135. The interesting thing about this is anytime you take sine and cosine of any acute angle, well, actually, we're going to find out any angle, it's always going to be a number between 0 and 1. So think about sine and cosine. You're going to have opposite over hypotenuse, right, and adjacent over hypotenuse. Remember that hypotenuse is always going to be bigger than the opposite or the adjacent sides. So if you get a number that's bigger than 1 here, that doesn't make sense. With tangent, that's okay because the hypotenuse isn't involved, right? So tangent could be a number bigger than 1. But sine and cosine will always, always, always be a number in between 0 and 1, okay? Okay, and so the very last thing I want to talk about is this idea of using the calculator, find an angle. Maybe, I said very last thing? I'm pretty close to the last thing. So I'm a little frustrated with your book because it brings in inverse functions without really saying that we have an inverse, right? There are some rules for having an inverse, like it has to be a one-to-one function that we talked about in college algebra. But really quick, let's just write about how we can find acute angles. So actually these functions are not one-to-one unless these guys are acute. So given that, so let's say that I know find theta given, this is just an example. I'll show you really quick on the calculator. So find theta given that maybe the tangent of theta, let's say, is 2.75. Okay, so given that theta is 2.75, let's go ahead and find the actual tangent of it is 2.75. Let's figure out what theta is, right? Look at what this is asking. One angle, when I take the tangent of it, gives me 2.75. Okay, so I'm going to come back to my calculator. Let's clear all of that out. And that's where these buttons right here come into play. So the inverse sine, the inverse cosine, and the inverse tangent. I should have done my nails, huh? I don't ever do my nails, so it doesn't matter. That's what these inverse trig functions are. So what this does, remember what this function, what tangent, sine, and cosine do is you spit in an angle and it spits out a number. So remember the inverse functions go the opposite way. So if I'm taking tangent inverse of something, what I'm doing is I'm taking the inverse of a number and it's going to spit out an angle. So in this case, if I want to find what theta is, if the tangent is 2.75, then I'm going to do second tangent. That's going to give me that tangent inverse. Oh, you can't see that. There you go. That's going to give me that tangent inverse, right? And I'm going to put 2.75. You really need to make sure you're in degrees when you're doing this, right? If I take tangent inverse of 2.75, I get about 70 degrees. So 70.02 degrees would be the angle whose tangent is 2.75. As long as that's an acute angle. There are other angles out there, but they're obtuse and they might be negative. Anyway, we'll talk about that later. But you know, like cosine inverse, excuse me. If I do second cosine inverse, I know that the cosine inverse of the square root of 3 over 2, right? Well, if I know that the sine of 30 degrees is 1/2, then the cosine of 30 degrees must be root 3 over 2. So yeah, that makes sense that we get 30 Okay, so you can kind of use your calculator to remind yourself of some of those values. That's really all I'm going to say about those inverse functions. For right now, we can use them to find theta, but it's much more complicated than that when it comes to talking about what it means to be an inverse. Okay. So find theta given that tangent of theta is 2.75. Using our calculator, we find that theta is approximately, right, 70.02 degrees. Okay, and we'll talk about what the radians mean another time. All right, here's the last thing I'm going to do because, oh, this is a record 45 minutes. This is why, kind of like I said, some of these sections take a while. I'll probably start breaking up these lectures. If we hadn't done some of that in class today, definitely would have broken up this lecture into 2 separate ones. A couple identities really quick. Well, let's just write these down. We've actually already talked about these a little bit. These are what we call the cofunction identities. Okay, and what this is basically saying is if I have 2 complementary angles, then their sines and cosines are the same. Their cotangents and tangents of those are the same, stuff like that. So like the sine, we know that the sine of 30 degrees, right, is the same as the cosine of 60. So that's true no matter what angle we have. So if I have theta, right, what is its complementary angle? It's 90 minus theta. Like, think about this. If 40 degrees is my theta, what would its complementary angle be? Remember, my complementary angle is an angle that when I add it to 40, I get 90. So how do I find that complementary? I could call that like theta primed. 90 minus 40 would give me 50. Okay, so what this is saying is that the sine of theta is equal to the cosine of its complementary angle. That's all these identities are saying. Likewise, if I have the cosine of some angle, then sine is its kind of cofunction, because when I take 90 minus that angle, that sine is the same. Okay, that's going to be the same. Tangent and cotangent are cofunctions when it comes to that. So this would be the cotangent of, and we'll look at these more later on. We have a lot of identities to get through. These are just kind of, you know, good to know. So this is equal to the complementary angle. And then what are the cofunctions? What are the friends when we're talking about this? You know, it makes sense that secant and cosecant would be kind of friends when it comes to this. Because what are secant and cosecant? They're just the reciprocals of sine and cosine. So it's kind of makes sense. I hope that makes sense. I'm just kind of throwing this in the very end. It's at the very end of your book also. But just wanted you to, you know, realize that. All right, you guys, 47 minutes. Holy moly, I enjoyed myself. That went really fast. But I don't know about you. I hope you enjoyed it too. I'm really excited that we're back together again. Please let me know if you have any questions at all when you go over this. And thanks for watching.